fourth missing basic is decomposition. And when we talked about the missing basics generally, we talked about the need to take big problems and decompose them into little problems. But the usual impulse for engineering students after a little bit of math science training is to look for magic bullets and equations of motion or the equations of electromagnetics. But most projects are too hard, too difficult to succumb to simple solution. If they were that simple, they'd already be solved. So when we talked about this earlier, we called it a failure of Descartes 101, and we'll say more about that in a minute. But why is this such a problem? Well, the problem emanates from the difference between problem-solving education and practice. In engineering science classes, we package problems in nice bite-sized little pieces so that the problem has routine structure and kind of a homogeneous nature to it. And that's fairly misleading when we compare those simple academic problems to the problems we have in a real world. So here we're depicting a statics book, and out in the real world of structures are much messier than the kinds of simplified abstractions that are depicted in our statics and structures books. So in real design, in real problem finding and real problem solving, we almost always have to engage in some sort of decomposition of that big, complex problem into a bunch of smaller problems. And then at the end of the day, we have to assemble those smaller problem solutions, sub-problem solutions, back into a unified whole. So that's what we want to talk about. And the way we're going to get into this is start, as we have in the past, from the Greeks. We're going to move to the French, and then we're going to come back to tortillas. So we've talked about Aristotle before, and Aristotle performed an amazing decomposition in the 4th century BC in Athens. He worked in all the major categories of what we now recognize as knowledge: logic, physics, biology, astronomy, psychology, politics, rhetoric, and poetics. And his decomposition still stands as a pretty good approximation to the college curriculum that we face. Now, we talk about decomposition as a failure of Descartes 101 because of that gentleman's famous book published in 1637 called Discourse on Method. And let's read a little bit of Descartes. It's a fairly short set of passages here, but it gives you a sense of what he was thinking back in the 17th century about decomposition. So what did he say? And of course this is translated from the French. But by these considerations, I was induced to seek some other method which would comprise the advantages of the three. Here he was talking about logic, algebra, and geometrical analysis, and be exempt from their defects. I believe that the four following would prove perfectly sufficient for me, provided I took the firm and unwavering resolution never in a single instance to fail in observing them. So what's he saying? There are four steps to solving problems generally. Well, that's a pretty big claim. All right, let's see what those steps are. Step one. Let's accept only those things that are true and that are beyond doubt. And how did Descartes say it? He said, the first was never to accept anything for true which I did not clearly know to be such. That is to say, carefully to avoid precipitancy and prejudice, and to comprise nothing more in my judgment than what was presented to my mind so clearly and distinctly as to exclude all ground of doubt. Now here we can say that Descartes being a little bit more mathematician and scientist than he's being engineer. In engineering, sometimes we have to move ahead when we have doubts because we're faced with solving a problem in the time allotted. But nonetheless, this first step is generally a good move. What did he say second? Well, here's the decomposition. The second, to divide each of the difficulties under examination into as many parts as possible and as might be necessary for its adequate solution. So this is the decomposition move. Now, how do we do that? Again, the moves are often linguistic or mathematical, but we take some big problem and divide it into pieces and see how that works. Step 3, move from simple to complex. The third, to conduct my thoughts in such order that by commencing with objects the simplest and easiest to know, I might ascend by little and little, as it were, step by step, to the knowledge of the more complex, assigning in thought a certain order even to those objects which in their own nature do not stand in a relation of antecedence and sequence. So he's actually saying, don't follow the steps of problem solving per se, but solve things easier before things harder. And that'll lead you to solutions to complex problems more quickly, because in part you'll learn from the easier solutions and know and use that learning in the solution of the more complex. Finally, and the last, in every case to make enumeration so complete and reviews so general that I might be assured that nothing was omitted. And again, thinking more as a mathematician and scientist, this is more practical in those fields than, say, in engineering, where again, sometimes we have to take some shortcuts in order to get the problem solved in the time allotted. But nonetheless, ideally, he's articulating something that's that has stuck with us for many years. Now, and then finally, he wraps up and says something to the effect that, well, therefore, the long chains of simple and easy reasonings by means of which geometers are accustomed to reach the conclusions of their most difficult demonstrations had led me to imagine that all things, to the knowledge of which man is competent, are mutually connected in the same way, and there is nothing so far removed from us as to be beyond our reach. So in other words, he's saying that this method, this 4-step method, is more or less sufficient for being able to solve the problems that human beings are able to solve. That's a pretty big claim, but it stood up. The ability to divide problems and solve those problems separately has stood a reasonable test of time. It may not be the only way to achieve solutions, but it's certainly been one of our most effective. Now, this is all fair, this is all well and good, and this was state of the art in 1637. But what does it mean for us now? What does it mean for us in solving a practical problem? And for us in this course, our practical problem has been the tortilla factory. So let's go back to the tortilla factory. How can we decompose the tortilla problem into smaller problems? And recall that in the tortilla factory, our job was to reduce the amount of dusting flour used in the tortilla line. So we're not going to do it step by step as that senior design class did a number of years ago, but let's take a look at their decomposition and examine the pieces of it and see if it makes some sense to us, to get a sense of practical engineering problem solving by using Descartes' decompositional method. So in the tortilla problem, there were really two parts. There was sort of an analysis part and an experimentation part. So that's kind of a methodological decomposition. And in each part, that was decomposed further. In the tortilla project, there was an analysis of product integrity reduction. That is, as the tortillas stuck, would they become elongated? There was a micro-analysis of sticking. So looking at the different places in the line where tortillas could stick. Would it stick at junctions of conveyors? Would it stick at the die cutter? And so on and so forth. And then there was an examination or an analysis of the consequences of excess dusting flour. So again, we've actually talked about some of this before. Too much flour in the air, gets burnt in the ovens, falls on the tortillas. So that was the analysis portion. What about the experimentation? Well, so the first part of the experimentation in this project was to actually measure the amount of dusting flour used. Now you might think that that's a fairly obvious step, but it was one that had not actually been accomplished in the company for quite some time. So it was the first and maybe the most important step in the project. And when that was done, they learned that the company was using twice as much flour than they thought they were. There were design of experiments tests to look at the effect of humidity and other variables on the amount of sticking. There was an analysis of dough texture. And then finally, perhaps the most important experimentation was to reduce the amount of dusting flour on the line until the line started to stick, and look where the sticking points were. And that showed where the critical path was in the dusting flour, and enabled the students to recommend places in which the flour could be reduced reliably. So this gives you a sense of how this kind of thing is practically applied in real engineering problem solving. So the bottom line here is that decomposing is a critical engineering activity. Almost all engineering problems worth solving are too hard to solve in with one big master equation, like sometimes we teach in some of our engineering science classes. We can't treat it as a monolith. We have to break it up into pieces, and we have to choose those pieces judiciously so that when we put it all back together, we've got a good solution to the problem. Moreover, this works not only in engineering problems, but it works in organizational problem solving and solving your problems interpersonally, working with people.